Okay, so I me stop the transcription. Fine. I guess I'm audible, right? Let me share my screen. Okay, so this is an extra session, and we will be covering. And tomorrow we have also a session for week 12. Okay, and it's just an extra session of 2 hours, and we will be covering the remaining part of reinforcement learning that we have up to TD learning. Okay, so yeah, so this is what we covered on week 11. I guess I've turned on recording. Let's check. Uh, Maximize this. Okay. Oh, so in week 11, what we covered, we revisited the Gridworld library that we had, and then we also did two dynamic programming uh, kind of algorithms. One is this value iteration and the policy iteration, right? If you missed it, you can just go watch week 11's recording on YouTube. Okay, and so it's mostly if you know the system dynamics, right? If you know the PSAS and RSA matrix, then you can and you know the policy. In that case, you can compute what is the value of that policy. And if you know all the possible policies, you can just go on looping through all the policies, compute their corresponding value. You can get a optimal policy with the maximum value. Or what you can do, you can instead of looping through all the policies, you can uh, like start with a random policy and then uh, kind of improve it, right? Improve it with like consecutive iterations until you reach a kind of a saturation point on the value. So you basically improve the value, right? And from the value you compute a kind of greedy policy. And I guess if you have attended the previous session, you know how to compute the policy from a value, right? You just from a q value function, you just take argmax, whichever action has the maximum value, you take that value, right? That's how you compute kind of an um, greedy policy from these value functions, q value functions, right? And q value function is nothing but where you have rows for states and columns are action, and you get value for each in each state. What is the value for taking action A, or let's say action B, right? How many, let's say finite action and finite state case, then it looks like a matrix of state cross action, right? So this is the part of model based reinforcement learning. So when you have the model of the world, and what do you mean by the model of the world? That transition matrix and your reward matrix, right? So how, what is the probability of transitioning to state B or state S2 with action B, right? If you know this, that means you know the world. Okay, and if you don't know this, that means you can interact, right? But you cannot, you don't know the entire dynamics of the world. So model means the transition probability dynamics and the reward dynamics, right? Okay. So if you know those two things, if you can easily go with value iteration or policy iteration, they can kind of give you a policy, right? Okay, on which policy you will have the best reward. Now comes the model-free reinforcement learning part. So today's objective will be, okay, I don't know the dynamics. I don't know the dynamics anymore, right? I only know, uh, okay, if I take this action, what is the next state I'm visiting? I only know this transition. So what I can do, just like a game scenario, right? Let's say you are playing chess. You have a setup, let's say a setup, and then you take an action, let's say move your pawn one step, right? Then you what you know, let's say if it you move your pawn one step and then there is nothing you can do to kind of weaken your opponent, right? So there is no reward or immediate reward. You don't get any immediate reward, um, but your next state is now the new chess board, right? The new setup of the chessboard. Now, in the next step, the opponent may try to, let's say, kill that pawn, right? So you will get a -1 in that state. And now, after your opponent take a move, there is another new state, right? So your action uh, to the world as and the next opponent is also considered as the world. So the transition is you take an action to the world takes some action or something changes about the world, right? In that case, your opponent is in within that world, right? So it also takes some action, adversarial action, maybe um, kill some pawn or something, right? And now you have either lost a point, or you have, let's say, you kill in some pawn or something of the adversary, right? In that case, you get a +1. So that is how the reward system works. So at a particular state, you take a particular action, you get a reward at a next state. Beyond this, you don't have any access. So earlier, I have the entire transition dynamics. So now I would also know that, okay, if I take action C, I would transition to the state 4, right? But here, until you take the action, you cannot certainly say that. You don't have access to the world. So it's exactly how the game environments work. Okay, so any online game or any, let's say, uh, game you play, right? Uh, let's say your temple run, right? Like how you move your phone, that is your action. What is the state? Uh, the what is the state? Your current screen, right? And based on that, you either swipe right or swipe left, right? And based on that, you either kind of keep on running, or you get caught by the monkey, right? Yeah. So unless you play, you do not know uh, kind of what will be happening next. You will have access to only the next step. Or let's say, if I just take multiple actions, like from starting to the ending of the game, if you just keep playing it, after the game end, you have this access to this trajectory. Okay, what were the states visited, and what was the corresponding reward and access, like actions associated with that state in my trajectory, let's say trajectory 1. Okay, and this is known as trajectory, right? Because it can change. So in my first gameplay, I may visit some state. In the second gameplay, I may not visit that state, right? So in different runs, I may have visited different sequence of states, and this sequence of states are known as trajectories. Let me connect my graphics pad so that it will be more useful. Okay. Yeah, just unmute yourself and uh, stop me whenever you find something kind of difficult to understand. Okay. Okay. Now see, there is some game. Okay. And now there is an agent who is, let's say, playing that game. Okay. And he is known as agent. So a agent. Now while playing this game, he sees, like, let's say he starts at S0, take an action A0, get a reward at 0, go to a next state S1. From S1, it takes an action A1 and sees a reward R1, transition to a next state S2. You get the pair, right? This is what a kind of interaction pair. So, yeah, this is what an interaction pair look like. Okay, and then from, so this is the common part. This is an interaction pair. Now next, this is an interaction pair. Third interaction pair would be like this: A2, R2, S3. So yeah, and when it ends, so let's say it keeps on interacting, right? And it ends at, let's say, S it's t minus 1, a t minus 1, r t minus 1, st. Right? T is the terminal state. So that the length of the trajectory is t plus 1, or you can kind of roughly say it is t, right? Okay. So this is called a trajectory, and it is, let's say this is trajectory 1. So how would I save it? It is, let's say, tau 1, and tau is the kind of data associated with a trajectory. So it's basically this entire set of states until the last state st. Okay, and then you can have another trajectory tau 2, third trajectory tau 3, and this is your history, right? You keep on playing your kind of strategy and see, okay, this is how much reward I gain, right? Based on that, you improve, or let's say change your policy. And what is policy? Just let's just remind it a bit. The policy is in which state you take which action, right? So policy 5 is actually giving you what will be the action given a state, right? So it can be represented as a, let's say, table, right? It can be S1, S2, S3. Let's say three states are possible, and only two action are possible, A1 and A2, right? So policy could be represented as a table also. So it should be, let's say, S1 take A1, S2 take A3, sorry, A2, and S3 take A2, let's say, right? So not a matrix, is basically an array, right? Yeah, in which state you take what action. Yeah. So if you follow this policy, this is what the trajectory would look like, and the trajectory may change, right, based on the environment. So based on the stochasticity, or how probabilistic the environment is, you might get a different trajectory different time. So if my system is deterministic, right, if my system has no noise in it, and what do I mean by noise in this case? Let's say you want to go to right, but there is a slippery floor. Then even if you want to go to right, there is a non-zero probability that you will end up moving forward. Okay, because there is a slip in the tiles, or even may you get fell down to the floor, right? Yeah. So basically, you loop back to the same state. Okay, either you go forward, right, like right, whatever is your intention, right? Our intention was to go, let's say, right. I can end up going forward because of the slip of the tiles, or I can fall down to the floor, basically looping back to the same state, or I can go to left also. So there are non-zero probabilities for other states to reach if my environment has a stochasticity or probabilistic nature. So that's why you can, with the same policy, with the same environment, you can have different trajectories of samples. Now let's see how I can sample these trajectories from our grid world environment. Okay. Now let's just consolidate up to that part. Okay, I can sample trajectories with some random policy. Okay. Okay. So just let me know if you find some part confusing. Okay. I am trying to kind of explain this one at a time so that it is not hard to understand. And you can see my screen, right? Can anyone just ping in the chat? Okay. Wait. Okay. Okay. Import. Let me just give you a bit zoom, right? Gridworld from Gridworld. Import uh, Gridworld. Let's just copy from week 10 or week 11, right? Let's just copy from week 11. A small environment or something like this. Or let me go to that. So you can configure that overnight. Okay, so we have the environment, and see, this is how you can interact with it. It's very easy. So, okay, so let me copy it from here. Okay, now see, we have defined an environment with sleep of 0.2. So there is 0.2 probability that it will not take the desired action. So you will get a different set of trajectories all the time. So even if you take action A, there is a non-zero probability, or basically 0.2 probability that it will take some other action, not A2. Okay, from A1, A3, and A0, it will take something randomly with non-zero probability of 0.2. Now, maximum episode step 1000 means you can only take up to 1000 interaction samples. Beyond that, it will terminate there. So basically, it's an game end scenario. So your game get ended, timeout. Okay. Now, what is this means? So for let's see, split cell and okay. Uh, my environment is pretty standard. What I can do, I can collect 1000 trajectories. How I can do it? See my current state. So I would be resetted to the state 0 if I call this environment.reset. So that means before each trajectory, I have to reset. So this is starting of a trajectory, right? And this is basically the number of trajectories or episodes. They're also known as episodes. So these are actually trajectories. Okay. Okay. Now done equal to false mean you are initializing that, okay, I am not done with the game yet. Done is false. While not done. So done is actually returned by the environment itself, whether you are done playing the game has ended or not. Okay. You render means you give a visualization how your agent is working. Okay. So you may, so whenever let's say you are implementing an algorithm, this is actually the computationally expensive part. So it's optional. So whenever you're playing it for thousands of times, right? It is better to not render it. So just comment it. Okay, but let's say for testing purposes, you want to see how the agent is doing, right? Then you can keep render for some amount of time, let's say. Or maybe you can render at some frequency that is over. Okay, after 10,000 rounds, render what is the emergent policy. Okay. So what you do, we take a random action. See, this is one function that is available with the package. Take random action, environment.random action. It will pick a random action from the possible state space. Possible state space is like left, right, up, down, right, on this in this grid. Now you step. So this is the standard API that is used with OpenAI Gym. So this library is there, OpenAI Gym. That is basically a gym environment for reinforcement learning agents. Okay. If you just go there are lots of agents. So me, yeah, these type of agents. Yeah, something like this. This Atari games or a robot or basically a car, a pole in a, so you have to balance a pole in a cart, something like this. So these all kind of environments are there, right? Also similar to Pac-Man or something like this. Since this Pac-Man environment is also there, right? So there is this kind of small ghosts that can reduce the life of this Pac-Man agent has to somehow eat all the fruits in the maze with avoiding this ghosts, right? Yeah, or you have to let's say balance something, or the snake robot, right? So these environments are there for you to kind of implement any reinforcement algorithm from scratch. Okay, and this Gridworld environment is exactly similar to that. So if you know how to use the Gridworld environment, you directly know how to use the OpenAI gym environments. Okay, now see, environment.step action. You step your action to the environment. Basically, you feed your action to the environment, and whatever is the connect, so what it returns, the environment returns the next state, the reward, and whether you are done, whether the gameplay is done. Okay, and info is something for debugging purposes. We don't use it that much. Okay, so what is the state transition pair? SARS prime is current state, action, reward, next state, right? And then your current state is your next state, right? So in the next interaction loop, your next state becomes your current state, right? You have now transitioned. So now based on your current state, if you want to take some informed action, right, or some machine learning driven action, your current state is actually your current next state. Okay, then you basically just to make it render slowly, it keep a sleep. It's not necessary. You can remove it when you are, let's say you are playing it for thousands of times, right? And then at the end you have to close the environment so that it gets all the resources that you are hogging in the system, it gets released. Okay, now let's see. I am rendering and playing for 1,000 episodes. Let's see. So time is not defined. I have to import the time. Import time, restart. Yeah, see. So this is how the game lets you interact from Python code. Okay. See, this is basically taking random actions. Okay, and basically from that it is receiving what is the next state, what is the reward, what is what, like whether it is done or not, right? And see, it's actually playing through multiple episodes. So whenever it is starting from here, that means it's a new episode. Okay, so you get the point. Okay, so this is how you kind of uh, write an interaction loop for Gridworld as well as for uh, the OpenAI gym environments. See, it's just, yeah. So it's basically taking random left, right, up, down actions, uh, uh, like from a random policy and seeing, okay, whether I am landing, right? And it's also printing what is the next state, current state, and all those things, right? Now, let me print only one trajectory. So if I just do one, then it is interacting for only one trajectory, right? One episode. Yeah, it's ended, right? And this, see, this environment dot close actually free up all the resources. That's why it become black. Now what I can do, I can just remove this, again do a restart and run. So you'll see the entire one trajectory, where it starts and where it ended. See, it is currently here it ends, right? So the trajectory was like this. So it ends at uh, at step 4. So this is actually fourth uh, it's actually fourth step, right? And you it gets a -1. So basically it reached here. It's reached here. So it goes to that spike. Okay, now again sample it. So how many states are this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 transitions, right? Now let's do another run. Oh, now it says seen a lot more other states than that. Yeah, now it stopped. So now it kind of almost 100 states it saw, right? 100 transition it saw. Now you get the variability of the episodes, right? They can vary a lot. And it reached here. So it reached at 31th state and get a -100 reward. That means it fall into this spike. Okay, it kind of fall into this spike. Okay, now you get the episode and all those things. And see, if I check the done variable, it is actually true now, right? So it basically ended. The game has ended. And if the info variable is, I can check the info variable too, right? It's actually whole. So it fall into a hole, or basically or a spike. Here it's a spike. Okay, so you get the idea how to sample trajectories with random environments, random actions. So where our agent will lie in this entire loop, right? Agent will lie this actions taking stage here. So basically the agent will, so if my agent is agent, agent, right? It will take the current state, right? And it will throw out a suitable action. Yeah, this is what my agent would be required. So my agent would throw out a suitable action and improve it action with more and more interactions. Okay. Now we'll see some kind of algorithms, how to design those agents. So just for others who join in a bit late, we are now not assuming that we know the world dynamics. We don't know the transition probability dynamics or the action dynamics, or let's say the kind of the reward dynamics. We can only interact with the environment. Okay. Now these are like kind of model free reinforcement learning algorithms. So you don't have to know the entire model of the world. You just have to have access to the interactions. So it's basically real world thing, game like thing. Uh, okay. Now let's see. So the algorithm that we'll be doing is similar to what model based was. Model based was like first you have to know some algorithm that can evaluate a policy, right? So you have to know, okay, if I want to evaluate how this policy is performing, then similarly you can loop through all the policies and pick the best, right? But that will be very much computationally expensive, right? So we cannot always do that. But anyway, for learning purposes, we have to know the algorithm. Okay, how we can evaluate a policy. If I know the policy, I can take lot of trajectories from that policy. And now, how would I estimate that how good is that policy? Right. So let's go to that. Oh, it's yeah. Let me restart. Actually, okay. Hmm. Okay, this is for model based. So model free notes are in my drive. Yeah, model free reinforcement. Download. Uh, okay, so it's very easy to understand. See, model free reinforcement. There are one method that is very popular. That is this Monte-Carlo method. Okay, so what is Monte-Carlo? You basically keep on collecting the data and then you aggregate everything, aggregate, compute all the kind of returns from every pair of state and then aggregate. Like that's the basically brute force approach. So what you do, see, so you basically generate these trajectories. So that's called experience. Okay. So your trajectories with a fixed policy pi, and this is for policy evaluation. So you have a standard policy or given policy. Okay. So which state, which action I should take at which state. And from that policy, you go and gather lot of experience in the environment, right? You don't do any improvement or anything. You are trying to evaluate how good is my policy. So you go on collecting experience, a huge chunk of experience, right? And then you do what? You initialize every state value function to be zero, right? You for every trajectory, what you do, you calculate return for every state, okay? And then you basically sum up all the returns for all the states. And after you sum up for the entire experience, you divide by how many times you visit that state. So basically an average, right? So for every state, what is the return you get? And then at the end, you divide it by number of times, how many number of times you visited that state, right? So basically you are computing average return from that state, which is value function. You get the algorithm, right? It's very simple. So you calculate return, you have this entire uh, set of set of experience. So those are nothing but arrays, state reward arrays. Actions are not necessary because you are following a fixed policy. So from that uh, array, so if I for this trajectory, for trajectory one, right? If I want to compute the return from S0, what I have to do? Let's say my gamma is 0.9, right? Then I have to sum like this: R0 plus gamma R1 plus gamma square R3, like dot. Similarly, if I compute, let's say trajectories for S1, I have to compute similarly. Here I have to also compute S0. So see, one thing I should remember, that a particular state can be visited multiple times, right? The mouse can kind of reach or loop back to the same state. So see, here it started with S0. Here it started with S1, but it reached to S0 again. Again, also like somewhere down the line, it might or might not visit S0 again. So there can be two options. I have to sum every visit or first visit. So I might only consider in a particular trajectory, right? I can only consider the first visit of a state and do not consider the rest, or I can consider every visit. So whenever a particular state is visited in a particular trajectory, I have to sum that return from that state, and I have to also keep track of, okay, how many times that particular state got visited. Okay, so after you exhaust all the experience, right, you have two values: the total return for a particular state for all the states, and the total number of how many number of a particular state is visited for all the states. And you just do a division to get the average return, and then you can output the value function based on that experience. So you have to collect a lot of experience, right? Let's say I collect 1,000 trajectories, and from that 1,000 trajectories I compute the total return, the total number of visiting per state, and then just divide it, get an approximate value function. Now see, I don't have to know the transition dynamics. If I know the transition dynamics, my value function computation is so easy, right? V is equal to I minus gamma p inverse R. I can just, I have access to P, I have access to R. I can just plug that equation, I minus gamma p inverse R. I would have the value function. But here I don't have access to that P or R. I can take action based on a policy. So this is how you can evaluate a policy. Now let's see whether we can, let's see whether I have implemented it earlier. Show you. Now these are so sample a trajectory give you tau. Okay, okay, we can do it. See, what is the sample trajectory function? Oh, oh, helper. It's in helper. Fine. So I have to import this. This is Monte-Carlo policy evaluation. So I have a ground policy which I want to evaluate. Gridworld.library.helper import. Okay, maybe I cannot import it from here. I have to read helper sample a trajectory. Okay, copy it. Okay, see what it is doing. It is returning you tau. Tau is what? Tau is this list of trajectories and a total return, right? Tau is what? Let's see. Sample a trajectory of our environment with a particular policy. Let's uh, take any random policy, right? Environment dot actions. Do I have the environment dot uh, policy? Okay, good. I can do a random sampling of policy. Just, oh, sorry, go here. Examples. Save value iteration load. Oh, not value iteration. Policy evaluation. I just take a random policy. So this is how you can generate a random policy. You just basically take random actions for all possible all states. Fine. Now, from my environment, this pie looks like this. So basically, in which state you take what action, and the mapping you already know that 0 means go right, 2 means go left, something like this. Okay. So you give the environment, you also give the policy and the gamma. Okay. The policy is phi, gamma is 0.9, that is, let's say by default it is 0.9. If I do sample, see what it returns. It returns me two things, tau and total reward. So tau, comma, total reward. And tau is what? Tau is actually the entire uh, this pairs S A R G. G means return of that state, and the done or not done. Okay, so it is not done actually, not done. So reverse of done, whether it is not finished. Yes, it is not finished, not finished, not finished. At the end, it will get finished. Is it not finished? So let me check. Mm, Examples. Unsafe. Sorry, it's unsafe. So unsafe, it is not important for us. Unsafe. Uh, okay. Anyways, this unsafe thing is not important for us. So we may like ignore it. Okay. So let's just modify our code. So the last one is unsafe. So I will just remove that part and also remove the marking unsafe part. Okay. So now we have only not done. Sorry. Yeah. Now we have only what? S, A, R, and G, and not done is not also. So that means this entire trajectory is ended when it reaches the end. It falls like at the end, it has a -1 reward. So that means -1 return. That means it fall to a spike or something. See, this R and G is different, right? G is basically your discounted reward and R is immediate reward. For the last state, the reward is what? The RT is the GT, because there is no further states. So that means your reward and the last state reward and return would be same. And this is for one trajectory. Now you can collect a lot of such trajectories, right? That's your experience. So let's collect a lot of experience. So my experience set, EXP, experience is what? Experience is a null array. Now for, let's say I want to collect thousand such trajectories, I in range 1000. Let's just keep the total reward 2. Okay. And let's just also keep the reward reward list. Tau we already have, experience you can append it. So with that particular policy pi, I can collect 100 trajectories and append it to the experience tau, and also in the reward list I can append the total reward for a particular trajectory. Now I have the entire experience. So this is how you collect experience for Monte Carlo. Okay. Now what is experience? Yeah, it's a big array of all the trajectories, all the 1000 trajectories or 100 trajectories I have visited, right? Okay. Now what I have to do, the algorithm, what was the algorithm? I have to loop through all the trajectories, track the NS and VS. So means how many times a particular state got visited. And then at the end, I have to just do a division, right? So I can have two dictionaries to track the total return and the total visited number, like number of visits, right? So I am currently doing every visit. So whenever I visit a state, I add it to the return, I add it to the number of visit dictionary. So N is this, and let's say total return TG. I just name it differently. Okay, now, but the algorithm here is kind of same VS. We are using the same like same kind of variable to keep track of it. Okay, so is obviously in program you can do it, but just for clarity I'm using another variable name called total return, TG. Okay, now these are kind of dictionaries. So these are sets, so let's mark them as dictionaries. Sorry, dictionary of dictionary, empty dictionaries. Now what I have to do, I have to keep on tracking. Now these should be default dictionaries. Okay, so there is a concept of default dictionaries from collections, import, default dictionary. So what they mean, if you don't have a particular value, I'm just, what I will be doing, I will be doing n equal to n plus 1 whenever I visit something, right? So that n value should already exist, right? To just basically dynamically adapt to that every state, I have to initialize that default dictionary. Okay, whenever you visit a unvisited state, initialize it to 0. So factory is what? Factory, my lambda would be 0. So my initial value for any unknown key is 0. Okay, same. Then I don't have to do it for n. No, I have to do it for n actually. TG is not that much problem. TG is actually also we have to uh, initialize it to 0, because I will be doing that TG equal to TG plus 1, TG plus GT thing. Okay, now these two are initialized. Now for every episode in experience, EXP, for every what was the kind of pairs we have? We have uh, yeah, this SARG, right? So SARG in episode. What you do, you so TG of S for that particular state, you plus it with G and number of visit, right? How many number you visit that state, you also plus it with 1. And now you basically look through all the uh, possible visits and return you have seen for all the states. After this, you have kind of a good uh, kind of estimate of what is the total return you see from any state and what is the total number of visits you have. Now you can compute an average. If I just do this, I just run this, it's over, right? Now n is this. See, it visited all those states and the counts are here. And you visit and see there are some states where you only visited once. So for those states, your value function estimate would be wrong. But the states that you have visited most of the time, in that case, you have a good estimate of the return from that state. So your value function estimate at those positions will be very good. Okay. So now TG is what? Total return from particular states. So these are the total return it shows from all the states. Now to compute the value function, we just do total sum divided by total number of visits. So what I can do, yeah, so value function could be another dictionary, right? So for every pair, so for let's just loop through TG, right? For total return, state comma total return, state comma total return in TG dot items, you basically do this. P state is equal to TG divided by NS. You got it? So basically you are doing a division for all the states. Now after this, you have a value function for the visited states. So this is how you evaluate your policy with 100 experience points with Monte-Carlo. Now this is for every visit, right? You are basically, whenever let's say you are visiting, yes, you are adding its return and adding its visit. So now you can also do first visit. So in a particular trajectory, you will only consider the first visit. Okay, that's another variant which has lower bias. So this implementation has a biased estimate of value function, which is proven. Then proof is not there in your syllabus. So you can prove that with every visit Monte Carlo, there can be a biased representation of the actual value function. So there may be. So what is bias? You already know from the initial classes, right? That means either my value function is inflated or it is there is a positive bias or a negative bias. So basically it is somehow inflated or kind of have lower value than the all the states are getting impacted similarly. Okay. So it's correlated with the state with the value function, but it is biased from that, which let's say there can be a 10-point bias. So it is plus 10 from all the states from the actual value function. This can be proven with the help of theory that okay, every visit Monte Carlo have some bias. To reduce that bias, what you do, you take in one trajectory, you consider only one visit of a state. So whenever you visit S0, you only consider that visit. Other visits you don't consider. So what you will do will basically for every trajectory, this one will create another default dictionary called visited. For this is for first visit. Visited is 0. So if I just query visited S, if it is not visited, that will return me 0. If it is visited, I will, whenever I visit something, I will mark it as 1. So what is the logic change? If visited S is equal to 0, that means it is not visited, right? It's visiting for the first time. I will update it in the computation and mark the visited to be 1. That's it. Next time this if loop, next time if S0 is visited, this if block would not execute. That means will not increment the total return of that state or will not increment the how many times that state is visited. So in a particular episode, only first visit is considered, other visits we don't consider. This is for first visit. If I just don't do this, it's every visit. So it will consider all the visits of a particular state. And if I just run this, now the value function estimate, it's in theory, it is less biased. Okay, you can go check out the theory if you like. It's there in the kind of the Stanford course that I follow, or even if you find any reinforcement learning literature, that is there. Okay. Okay. So this is how Monte Carlo policy evaluation works. Now see, I have a random policy, right? I can always go with uh, that policy, right? That give me all combination of policies, but that would obviously for this environment it will take, we previously we computed that it will take around 10 to the power 50 gigabytes to store, right? So it is not possible to store like all policies, but for a small environment it is doable. So for an environment with 4 states, my possible policies would be 4 to the power 4. That is how much 4 to the power 4 is, let me check. 4 to the power 4, right? It's 256 policies. So I can obviously generate all possible policies, get a good amount of experience, and identify whichever policy has the maximum value, right? And we can do it. So let's just build a small environment and do that, right? So a small environment that earlier we created was this, right? Not even this. Let's go with an even smaller environment. Here, this is the smallest environment we have. So okay, let's just put everything together now. This is my environment creation part. And instead of this world, I am considering the small world, right? And all the possible policies there are can be, yeah, computed with this iter tools product function, right? Yeah, the possible policies, yeah, the combinations are this. So all possible policies are this. Um, get it, all possible policies. So here I can write all possible pi and see how many pi's we have at this point. All possible. This is like not that much. If I just check save, is actually 256. There are 4 states, so 256 possible policies. Okay. Now what I can do, instead of generating a random policy, I can just loop through all the policies and collect experience, uh, compute the value function and get average value function. Based on that, take whichever policy has the maximum value, right? So everything remains same, just an outer loop for pi in all possible policies. Oh, sorry. You just indent the entire thing. So you collect experience to, let's say, first visit Monte Carlo, get the value function, and from the value function, you get the mean value function. Okay, so v dot values dot mean. No, let's pass it to np dot mean of the values that you get, right? So that's the kind of estimate average value function for a particular policy pi, and you can keep track of these values, right? Values, I value. I value is equal to a list, and then basically you append this pi value dot append. Yeah, so you have the list of policies for a particular pi, you have the corresponding value function stored. Now if I just loop this and see, we are collecting only 100 episodes, right? And we are looping through all the possible policies. And see, we are not considering any dynamics. We are taking action in the environment and based on that evaluating how good or bad is my policy, right? So run. What was the problem? Oh, okay, so we cannot do mean. Maybe we have to cast it to array first. Eh? Okay, unsupported operator divided by built-in method for integers. So what is this v dot values? I guess you have to call it. That's a method. Oh, it's a method. So I have to call it. Then I have the value. Okay. Okay. So let's see. So see, this is a very small environment, right? So taking maximum steps 1,000 doesn't make sense, but let's keep it. So we are collecting 100 samples for particular policy pi, then computing whatever the value function with Monte Carlo. So this is Monte Carlo method, Monte Carlo. And based on that, we're computing the mean value function and put also storing it. So just to see, okay, which policy has how much mean value function. What was the error? Let me check. Okay, sorry. I have to um, cast it to a list. and then take the mean. Okay, now I have for 253 value function 253 policies, I have the 253 estimated average value function. Now let's see what is the maximum. Just what we did earlier, right? We take whatever has the maximum value and then yeah. So this is the pi value. Max pi value is what? This, and then what is the index of that max pi value? Here it's 96. So my all possible policies. If I take the 96th policy, this is my estimated that okay, this is my best policy so far, right? Now let's see if I can play as human and then pass this policy. Yeah, this is the policy. See, it is the optimal policy. So if I go down and I take right, that's what my kind of optimal policy look like, right? I have to go down here and then go right. So see, I can still loop through all the possible policies and apply that Monte-Carlo policy evaluation method and see how you can kind of keep on interacting with the environment and estimate kind of a wait, let me okay. You get the overall idea, right? If I can evaluate a policy, I can loop through all the policies and get a kind of and you can also see for each policy what was the import matplotlib dot pylot as plt dot oh okay. Is it did I restarted it? Okay, maybe I have restarted it. I have to run again. Oh, sample registries. I have to so do this. Okay, okay. Now it is 80. As it is different all the time, right? Now see the 80. Now it is 80th. So if I just replace it with 80, what was that policy? It's the same policy. Okay. So maybe these two states, which are not like these are don't care states, right? They have different uh, values. Yeah, they have different values. Now, if I do plt dot plot I values, you can see oh, plt dot plot I values. You can see this is how my value function estimate has been changed. So at this point, my maximum lies somewhere close to 80. So this peak. Okay. Now this is not a good approach. Why? Because if my number of states are more, then creating all possible policies is not an option. So we checked that okay, if a 95 state environment with 95 state environment with 4 possible action, right? My all possible policy can grow up to 2.3 into 10 to the power 49 GB of space. It's not a good approach. What is a better approach? Let's just see what is the next algorithm we have. So next is instead of doing this entire thing after so instead of storing the experience, what you can do just to see, just to optimize the memory utilization of the thing, what you can do, you can update the value like this value function and the number of counts as you keep collecting data. So you don't have to store the entire experience together. You have to just store one trajectory to compute its corresponding returns, update the representation. That would be efficient in terms of memory utilization. So you don't have to store a lot of experiences. You can update your value estimate and your value estimate basically just after seeing one trajectory. Okay. So what was the update rule in that case? See, it's really simple. So currently we are doing at the end, right? After you store everything together, then you, at the end you are dividing it. Instead, so basically this is an offline algorithm. You do the computation offline. You online, so whenever you are playing, you do nothing. You just collect data as much as possible, right? So in the code example, we collected 100 trajectories and then we run our algorithm. So this is basically an offline thing. After you computed all the trajectories, you run your algorithm, you compute the VSS, and then you move to the next policy and collect experience again. So the next algorithm that proposes an online method of doing the same thing. So Monte-Carlo updates with online. So you don't have to wait to collect 1,000 experiences and then update your value function. Rather, you can do it as you go, as you keep one trajectory, you get the value function, get the returns for all states, you update, then move to the next episode. So you don't have to store the entire experience. So you are optimizing in terms of memory utilization. So what is the update rule? And these are very important. So this is the basic rule for Q learning, which is like a famous algorithm in reinforcement learning. We'll cover it. See, so what is average? Now, so let me just uh, give you this mathematical representation is very easy. So what is my notepad here? Okay. So let's say I have a value function v vs v wait. Okay. So I have a value function called vs, which is let's say true at this point, and the number of states I visited is ns. So basically, value function is the average return after you visit n number of time that state, right? Now let's say a new return I got gt for s I got. Now how would I update my value function? Directly online. So I don't have to wait. So how I can update? So what is the total value? Total value is what? Average. This is average times how many number you visited ns. Right now you visited again and get a return NGT. So you basically visited again and get a return. So how would I update the value function? So this is the total till ns, right? Now plus the current return that I got. So now it's the new total. And what is the total number of visits now? This is the new total, right? And the total number of visits is ns plus 1. This is the updated value function. Got it? It's pretty easy. So basically, you compute the earlier total reward, total return. You add the current return you got, and you also update with the new updated number of visits for that particular state. So let's just simplify it a bit. So Vs is equal to, and this equation is widely used. So what I will do, mm, Vs plus Gt. So okay, so this ns can be uh, so let's just do it like this. So ns divided by ns plus 1 ps plus 1 over ns plus 1 into gt, right? So now you do some math. What you do, you do like this: ns plus 1 minus 1 divided by ns plus 1. See, the nominator is same, right? I'm just adding plus 1 minus 1. Vs plus 1 over ns plus 1 gt. Now here I can simplify it with Ps minus 1 over ns plus 1 Vs plus 1 over ns plus 1 gt. Right? Now just take this as common. Basically, your update equation looks like Ps plus 1 over ns plus 1, and you take what? You take gt minus v of s. This is your new update equation. And see, these are known, right? This ns plus 1, ns I know, vs I know, new return gt, it will be coming from the sample. And based on that, I can just update my current state without waiting for the entire episode. Now let's just implement this. This is too easy. Okay. So by doing this, what are my incentives? I don't have to store the entire experience now. I can just update the same code. So let's not override the code. Uh, yeah, let's just do here online Monte-Carlo paste. So same, I am looping through all the possible policies, or initially let's not loop through all the policies. Let's sorry, let's choose a particular policy or a random policy. Yeah. First, let's go for a random policy. The random policy, I can choose it like this. Here, my random policy is there. What I am doing, I am collecting trajectory. No, I don't want to collect trajectories now. I don't want to store the trajectories. I want to update the trajectories as soon as I am kind of observing them, right? So everything will be same. So trajectories, I get a tau. I don't store it. This part is not required. This reward, I don't care. Not useful for anything. Tau I have. So this nj, these things I should keep over top. Now for this tau, right? Yeah, this loop would be going inside. Yeah, and this tau is basically the trajectory, right? Tau. And let's just do every visit first. So you are visiting every state. So this entire part is not required. Yeah. So what you do, you collect a trajectory, get its tau, all the possible pairs S, R, and G, then update your representation based on it, right? And the update equation is uh, directly, you don't have to track TG anymore. You can directly update V. So Vs is equal to Vs plus 1 over n plus 1. So 1 over, or just let's just do some optimization. Let's do n plus 1 at the beginning and then do just n, right? 1 divided by ns times gt minus bs. So gt is g minus bs is b of s. You get the idea, right? So now see, I don't have to store the entire experience. I can just collect a trajectory, update its value. So it's optimizing my memory utilization. And I don't have to do this also, right? I don't have to compute the v separately again. I can just do this. Okay. Now, okay, let's evaluate for this pi once. Oh, sorry. Done. So v is these two states. So that's small environment, right? Now I am still going for 100 like 100 episodes, but I'm not storing them. I am just collecting one episode or one trajectory tau and then updating my value function. So it's an online method. It doesn't rely on storing the experience. Okay. Now let's go with the entire thing. This p value. Let's see whether it converges to the same thing or not. Sorry, not this. Oh, and also do first visit. So first visit logic would be exactly same. So after you visit, so this is policy pi. So this pi value append will be here. After you like visit all 100 trajectories, you update your pi value for that particular policy pi. Okay, you get the idea. Now you are not storing the trajectories. If I just run, oh, why it is getting an error? Oh, this should be indented. So now we are doing first visit online Monte Carlo. Every visit you already saw. They just have to comment these 3 lines. Done. Now, if I see the pi values, I can also plot them. Plt dot plot. Yeah, this is my new estimated pi values. And similarly, I can compute the max and all those things. So what is the index of the max? It's 56. If I, what is the maximum value? 88. And all policy is pi. It is 67th policy I am currently seeing. env dot play as human. Yeah, this is again the correct policy. Right? And see this these two policies are actually, so these two actions are actually important. The other two can vary, right? It doesn't have any impact on the value. That's why your the index is changing, like whenever you run it again, the index may change, right? Because these two can have any we don't care about their actions, right? There can be same value for 2, right? So put pivot. So there can be 16 possible policies with the same value because we don't care about these two actions, right? We only care about these two, right? Okay, so you got the idea. Now, what was our improvement in this case? We can update without storing the entire experience. Now we are going to so now we are going to improve that. Okay, it is not possible to loop through all the policies in a large environment. So uh, what I can do to not loop through all the policies, rather I can improve on a initial policy. I will not loop through all the policies. I will initialize with a random policy maybe, and I can improve on the next run. I can improve on the next run, and possibly it will be a monotonic improvement. So earlier logic, right? That you can, so if it is a contraction operator, it will reach the optimal value function eventually. So you will stop when your value function converts. That thing. So so the kind of limitation of these algorithms are, so they can only work when the number of policies are iterable. So there are finite number of policies or whichever we can store. But when the policies grows like a larger, right? For example, a 96 or 95 state environment uh, would require 2.3 to 10 to the power 49 GB of memory to store the possible policies. It's not solvable in those scenarios. So what are the next improvement that we can do? That okay, we don't have to loop through all the policies. We can start with something and then improve that policy by improving the value function. Then again improve that policy over that policy you can improve again. Again from the third policy you can improve again, so that we don't have to traverse through all the trajectories. Rather we will basically see here it can go down up like this, right? But in that case I can only go up, possibly probabilistically I can go only up. So in that case I have to traverse a lot less number of trajectories. So in last class we observed that instead of traversing 10 lakh possible policies, we can do it in value iteration. When you know the world dynamics, right, you can do it within 160 iterations. So 160 improvements, you can reach the optimal policy instead of traversing 10 lakh policy possible policies. That's very efficient when you know the world. But when you don't know the world, there comes a challenge. So earlier, when you know the world, you can take a greedy update. Basically, you know the value, estimated value at all states, all actions, right? Then you can take a greedy update. Okay, I know the entire value function, I can greedily choose whatever action I will do. That's why we're doing that argmax operation. But here, the game is a little bit different. So you have not visited some states till now. You don't know the entire. So let me just explain it a bit, then it will be more clear. Now this part you know. Now comes the temporal difference learning part, the last part of the reinforcement learning topics you have in this course. Okay, so there are two methods, RSA and Q learning, we'll say. Okay, so where is the here? So let me just do this temporal difference learning, temporal difference part, and then I will explain how to improve the policy. Okay. Okay, what is the okay here? So see, this was my earlier update equation. This was my earlier update equation, right? Now, return, what was the equation of return? Return is equal to GT is equal to what? RT. So now what we are doing, see, current initially we have to see the updates. These are like really important. We have to store the experience. This was the offline method, right? Now in online method, have to store the trajectory or episode trajectory, right? Now still we are storing something. Maybe the trajectory is infinitely long, then my memory requirement will go infinitely long, right? If I have to store the entire trajectory. If let's say the trajectory itself is 10 lakh transitions long, then that's not possible. So the next update come is immediate update. So what we have to do, we have to update the value function as soon as I see this transition S A R S prime. I want to update my value as soon as I see this transition. So in that case, I don't have to even store the trajectory. I can directly update my value after seeing a transition. After seeing the next transition, let's say S prime, A prime, R prime, S double prime, I would do another update. And I just forget this thing. I just update this and again forget this code, the next update. This is called immediate updates. Now my requirement of storing the trajectory is even gone. Okay, so how we can do it? We would approximate the return. So why we are storing the trajectory? Because we have to compute the returns, right? And for the computing return, we have to know the entire trajectory to do it from S. What are the like sequence of rewards we observe, right? So we can approximate this. Let's just write the equation part. So at t plus gamma at t plus 1 plus gamma square at t plus 2 plus dot till end. Now see, I can is equal to, I can also write it like at t plus gamma will be common at t plus 1 plus gamma at t plus 2 plus dot 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 somewhere. So this eventually I can write it with at t plus gamma gt plus 1, right? And then that approximation come into picture that now gt is a high variate estimate of what? Value, right? Value is what? Value is basically expectation of gt, right? The average gt. I can replace this with value. That's the approximation part. So your new update equation at t looks like at t plus gamma v st plus 1. So your gt can be represented as this. And this is known as the temporal difference learning method. So what you do basically, you basically do a bootstrapping. So this is your approximated GT that you put to compute the current GT. Okay. So now your update equation similar. This update equation, how it looks now. VS, this is a very good looping structure. VS is equal to VS plus 1 over NS plus 1 at T plus gamma V ST plus 1 minus V of ST. And you basically do TET here. This is your new update equation. Basically, what you do, you replace the GT with the temporal difference. So this is called, in theory, this is called TD target. TD target. So it's basically an approximated version of return with the value function. And this is used. So this is basically temporally different. This is kind of following the temporal structure of the environment, right? So ST, then you take AT, you got some reward at T, and then you transition to ST plus 1, right? So basically, this is the temporal structure that it follows. That okay, the current state would have a return of at T plus whatever average return you got from here. So basically, V of ST plus 1, you keep it here, and then you factor it to gamma plus with the current state. That would be my current return, possible return, GT. So basically, the equation is built following the temporal structure of the interactions. One minute. Okay. So that's why it's called TD learning, and this target is called TD target. And see, another approximation sometimes is applied here is n plus 1, right? If n is, let's say, very big, right? And because you are keep exploring the environment, keep interacting with the environment, this ns becomes very big quickly. So if you, let's say, uh, go with 10,000 episodes, right? Interaction episodes, and mostly, so for example, in like 2020 14 deep reinforcement learning papers, the interaction episodes are like 15 million, 60 million, 1,000 millions episodes. Okay, so in that range, this 1 over ns plus 1, this quantity becomes very small, almost tends to 0, which actually hampers the update of the VSP. So basically, if this quantity is close to 0, right, that means my value function would not get updated, right? So to keep my value function up, like keep updating my value function, we basically consider this entire 1 over ns plus thing to be a constant called alpha, or learning rate. So in naturally it should go decaying like this, right? As you go explore the environment more and more, this learning rate 1 over ns plus 1 should go to 0. Okay, go to 0. But to keep learning, sometimes we we kind of follow a we kind of keep it constant. So for 1 over 100 also, right? It's almost 0.01. So it decays really quickly. So not like this actually. It's something like this. This is how the 1 over ns plus 1 curve can be drawn. So it's actually decay very rapidly. And it, let's say, goes to almost zero very quickly, right? So to kind of relax this computation, what you do, you basically replace this entire thing with a constant value. So a constant value can be 0.001. That's your alpha value, alpha or learning rate value, right? So after all this modification and all, the final equation looks like this for TD learning. ST is equal to V of ST plus alpha at T plus gamma P of ST plus 1 minus V of ST. Alpha can be some small value. And see, now I don't have to even store the trajectory. I can do this update as soon as I see ST 80, I take some action 80, I get some reward at T and I transition to ST plus 1. As soon as I see this transition, I can update my value function representation immediately. I don't have to store the entire trajectory. Even I don't have to compute the return GT, which is computationally expensive. Okay. So this is called TD learning. Okay. Now let's just modify our code same. So we'll loop through all possible policies and compute our VS representation without storing the trajectory, only by interacting with the environment and seeing this kind of this small tuples, right? So ST, AT, RT, ST plus 1 tuples, and update my value representation based on that, right? And let's see whether we can find the optimal policy in that small environment. Okay, let's you see the gradual update in theory, right? So first of all, people think about, okay, what I can do in a brute force approach. Now they thought, okay, now I don't have to store that much in memory. What I can do to online compute the same thing without storing the entire experience. Now they are like trying to optimize it even more that, okay, I don't want to store the entire trajectory now. I can only store the pair and update my representation somehow. So this is the TD learning and all after all optimizations. So now I hope you are enjoying the thing. So now let's go with the TD learning, TD learning, right? So what you are supposed to do, let's just go with a random policy first. Oh, sorry, I have to. Yeah, this is the environment, small environment, random policy I have. Now let's just get this thing first. Okay. Now I don't want to sample the entire trajectory. I just want to interact with it, right? So let's copy the previous loop, this interaction loop we had initially. So reset till here, it is a episode. Oh, sorry. So instead of sampling this, we are currently interacting, and we are interacting with some 10,000 episodes. Same for all the algorithms, we are interacting for a particular policy for 100 episodes. But we are not like, for some cases, we are storing the entire experience, we are storing the trajectory, or we are storing nothing. We are storing the transition pair. Okay. Now this is the trajectory loop. So you reset to the initial state. You do done equal to false until it is not done. You don't render. For example, you don't render because this has a lot of computational overhead. You take some action with that policy. So I have my policy pi. So let's just not include them for now. Let's just put everything. Oh, sorry. Fill here. I have the policy pi here. While not done, fine. I take an action from the policy pi. So pi, whatever state I'm currently in, right? So current state. So this is an array that gives me actions back. Okay. So current state, I give it a current state, it gives me the corresponding action. Fine. Now I will strip that action to the environment. Now I get next state, reward and not done info policy. Not done info, right? So the transition pair I have is state, action, reward, next state. Done. Now what will be my update equation? I don't need this in, because I will be using a constant alpha value, right? I'll be using a constant alpha value. So let's I'll keep alpha to be 0.0001. Oh, that's 0.01. Okay. Okay. Now what will be my update equation? P current state is equal to P current state plus gamma. I have to also define gamma. Gamma is equal to 0.99 or 9. Gamma times, is it no, not gamma, alpha. Alpha times current reward plus gamma times V of next state, right? Minus V of current state. You got the equation update equation similar to this. VST is equal to VST plus alpha RT plus gamma VST plus 1 minus V of S. So this is the entire update equation. Now you transition to the next state. Don't do sleep. I don't need this. I'm not rendering it, right? So they don't need sleep formatted a bit. Okay. Now it prints the transition update. Let's just not print the transition. Okay. Next step. Now these things are not required. After you traverse through all the experiences, you have your new value function estimate. As you are not storing the trajectories, you are updating the value function as you are going along, right? After the end of the 100 plays, you basically get your mean value function and append it to the pi value. And currently we are not looping through all the policies. So let's see what is the problem. Default dictionary is not there, so I have to import it. Done. Now value function v looks like this. Okay. Now let's look for all the possible policies. So what is the all possible policy we have? This eta tools. This. Now instead of one policy, I can just look through all the possible policies. Pi value, pile on possible policies. I just indent this. Also uncomment this, indent this. Now see, I'm just looping through all the. I'm not collecting experience anymore. I'm also not doing every visit, first visit. I'm basically starting a trajectory, updating my value function as I am going on, and collecting playing with a particular policy for 100 episodes. Update the policy, update the value function based on it, and then at the end, I'm appending that value function for that particular policy, mean value function. Now, if I just run this over, now let's plot. matplotlib dot pyplot as plt dot plot your py value. So this is the kind of, see, all the value function that we got, they are exactly same, right? Somewhat biased. Sometimes it's a bit biased, sometimes it's not biased. See, it's a bit biased, right? But the shape is same. See, at this point, it is ranging from -3 to 2. Earlier, it was ranging for -100 to 75. So they are in different scales, but they represent the same structure. So now if I just do the same thing with whatever has the maximum, whichever index has the maximum value, get the policy, all possible policy of the 90th, 98th, right? And then just play, add that value, play as human. Okay, it represents the exact same policy. Go down, go right. Okay. Now you get the kind of overall idea how these things work. But the now also the problem is what we optimized. We optimized uh, kind of the value computation, right? We still have to loop through all the policies. So the next optimization. So what are the optimization that we done so far? We don't have to store the entire experience. We don't have to store the entire trajectory. We can only store the SAR S prime tuple and then update my value. Based on that, I can loop through all the possible policies and kind of get an estimate of the value function, right? Whatever is the best value function. Now the next update is, can I not loop through all the policies? Rather, I start with something and then I keep on improving on top of that, so that I don't have to traverse. Basically, I don't have to traverse to all these policies. Rather, let's say I start here, I directly jump here, and then I directly jump here. So in 3 steps, I will be reaching to the optimal value function. And for basically 3 iteration, I will be having the best policy. And those are known as this Q learning, SARSA, these algorithms. So today's objective was to go up till TD learning. So SARSA and Q learning, maybe we can address them the next week. So I hope you enjoyed it, right? So now, see, we don't even need to know the environment anymore. We can just, we don't have, we just have to know how we can interact with it. Based on that, I can solve it. Okay, given my all possible set of policies are, it can be stored in my laptop. So if my laptop has 2.3 into 10 to the power 49 GB of RAM, I can even solve that 96 environment, uh, in 96 state environment with this method, right? The next part is to now how I can do control. So how can I uh, start with in random, or let's say a suboptimal policy, and I can improve my policy based on my experience. So rather than traversing through all possible policies, I can just keep on improving my initial policy until I, let's say, reach some criteria. Let's say my value function converge or my policy is saturated, is not changing anymore. Okay. So those are there. So there are 3 algorithms, which will be the kind of last of this reinforcement learning part, which will be Monte-Carlo policy evaluation. You already know, right? Now this will be Monte-Carlo policy control. Okay. So basically an evaluation part and then an improvement part. And the evaluation would be on Q function. It's very easy. I can, and maybe we will not kind of implement those, just just by going over them, it is enough. Okay. So Monte Carlo policy control, or let's say first step is evaluation, and then you do some improvement on top of it, and then loop for the next iteration. And then there is this epsilon greedy policy concept. Yeah, Monte Carlo control. temporal difference, SARSA, and Q learning. First, that's our end of reinforcement learning. Okay, so it's quite a bit of material for the next day. Maybe we'll cover it. Okay, and these are really good algorithms, so you can solve larger environments without even let's say looping through all the policies. You can solve it. Let's just do a kind of wait. Let me. Is there policy D key when is there? PO SARSA, SIP SARSA. And maybe we'll just keep it for the next day, right? It will be better if we keep it for the next day. But too much information for one day. So this is so the next day will be how I can not loop across all the policies, rather start with something suboptimal and then improve on it. Okay. So and that basically transitions to um, instead of going through 10 lakh possible policies, I will just let's say only visit 160 or around 200 policies at max, and you still reach the optimal policy in a large environment. Okay. Okay. So I will share these notes and everything with you, even today's code up till the TD learning. Okay. And these are extra. So the TD learning is the last thing that you have. Okay. So this SARSA and Q learning, these two topics are basically extra just to kind of give you an edge on reinforcement learning so that you can, so if you want to study this kind of this theory later on, it would be kind of a like start, like head start on this, that okay, now this is how I can implement Q learning on a grid world. Okay. And so there are so after this is the end of classical reinforcement learning. Okay, so after this there is this entire new area called deep reinforcement learning, which obviously I will not cover in this. So in that case, the advantage is you are not assuming that the state space is finite or the action space is finite. So your state space, action space can be anything. So it can be, let's say, image, right? Image. So image still is finite because one pixel can only have 255, 255, 255 value, right? Max. So in combination, you have 255 cross 255 cross 255 combinations for a particular pixel. And let's say you are representing it with a 64 cross 64 cross 3 image, your state, right? Then you have a finite possible number of states. Still, it's very large. So either your state space will be very large or your action space can be continuous. So instead of going left, right, up, down, your action space can be how much force I should apply on a joint of a robot. Okay. Or let's say how much throttle I should apply in a quadcopter. So those are continuous values, right? Continuous actuations. Okay, I want to apply 2.3 Newton of force, or let's say 2.3 something thrust, 2.3 unit of thrust something to the helicopter so that it can fly stable. So those are covered in the deep reinforcement learning literature. How I can scale these theories and use neural networks to basically scale things up when there can be infinite number of state space and infinite number of action space. You see, you cannot store the infinite number of state space in a table, right? The memory requirement you cannot satisfy. That's why we rely on neural networks that acts as a function approximator, or basically a function that can give you access to that virtual table you have. So you plug in state at some end, you get uh, a state and action at some point, and then you get basically the value corresponding to that entry in the table, in the large table. Okay, and those things I can will not cover here. Maybe later on I can uh, make another course of this. Okay, or maybe I can take the reinforcement course later on in NPTEL itself. Okay, basically I can do TS. I'll apply, let's say, in the next semester. Okay. So guys, I hope you have enjoyed like how we can do gameplay kind of stuff and still know which policy is best. Next day, I guess we'll do these two optimizations. Okay, how I can improve one more policy and then kind of conclude this course. Okay, prepare well for your like and final exams. Okay. So your theory part will be up till TD learning. So focus on up till TD learning, not whatever is beyond that. Okay. Bye guys.
Thank you, sir.
Yeah. Thank you. Stop sharing, stop recording.
Thank you, sir.
Yeah. Thank you.